Hello and welcome to Ask the Expert webinar session. My name is Atul Dev and today I'm going to talk about interface modeling using Altair Radioss version 2021.2. So what is contact, or what are the typical applications of contact or interface modeling? So the interface or contacts are defined to avoid the intersections of different parts into each other in the event of crash or any impact or the physical interaction between the two parts. So basically it gives you the right physical behavior or the phenomenon. So there are various types of contacts that includes node to surface, surface to surface, and the self contact. So in the node to surface contacts, the slave is always nodes and the master is surface. In the surface to surface contact, both master and slave are the surfaces. In the self contact, you define master and slave on the same component, and then at the same time that component is master and slave. So this table shows the general library of mostly used contacts in Radioss. So these contacts are basically divided depending on their stiffnesses. So there are nonlinear stiffness contacts and linear stiffness contacts. In nonlinear stiffness contacts, there are type 7, 11 and 19. And for the linear stiffness contacts, there are type 24 and 25. Type 7 is general purpose contact. It is usually node to surface contact and you can use it for any application. Type 11 is edge to edge contact or line contact. Type 19 is combination of 7 and 11. So most of the time you end up defining type 19 contact. It gives you advantage of using 7 and 11 at the same time. In the linear stiffness contacts, there are 24 and 25. 24 is widely used in electronic modeling with solid elements, or the typical applications are press fit. Type 25 is general purpose contact. You can use type 25 in any application, but it is linear stiffness contacts. So we are going to see what is linear and non-linear stiffness contacts in the coming slide. Moving on, let's move to non-linear stiffness contacts. It is node to surface contact. And as we saw in the previous slide in the table, we have type 7, 11 and 19 for non-linear stiffness contact. Let's look at type 7 contact, which is nonlinear stiffness contact. When we say nonlinear stiffness, which means the stiffness of the contact is depending on the rate of change of penetration and the stiffness is not linear. So here in this figure on the right top corner, K is your instantaneous stiffness and that is changing as penetration changes. So this is simple example of type 7 contact, how the gap is calculated, and the important thing is type 7 contact works on the penalty method, and there are various options for defining the variable stiffnesses. So the gap is calculated using the main segment and the secondary nodes. So this is your contact segment, and that gap could be you can keep it as a constant gap or you can keep it as a variable gap, and these resistive forces are applied to keep the secondary nodes out of the contact. So when this slave node tries to penetrate into the contact gap, there will be resistive forces applied on that node to keep that node on the contact gap. So since it is non-linear stiffness contact, it will be governing, or it will control the time step. So in order to stabilize the simulation along with the nodal time step, you can introduce interface time step. So there are various situations or conditions when your type 7 contact doesn't help or it is not working properly. So usually it happens when there are edges involved, just shown in this picture. For this edges, type 7 will not work. So in order to make it work, you can define type 11 contact. So type 11 contact works just like type 7 contact. So, and it, when I say it just works like type 7 contact, it will consider the same penalty formulation, same gap definition, and the search method. And the general practice is when you're defining the global contact with type 7, you always have to define type 11 along with type 7. Let's look at interface type 19. And as I said earlier, type 19 is the combination of type 7 and 11. So this contact is just one input for surface to surface and edge to edge contact. So surface to surface contact will be defined using the surfaces, and it is referred as /surf. And edge to edge, for edge to edge nodes, it uses the nodes using the /surface, and that can be controlled with the iEdge option within type 19 contact. So what is this iEdge option? So when you have iEdge equals 1, the only external edges of the surface will be considered for the contact. So as shown in this figure, only external edges of this surface are taken into consideration for the contact. When you have iEdge equals 2, it means it considers all the edges of the surface. Now you can see here all the edges are considered for the contact. So this type 7 type 19 is type 7 plus type 11, and for having that type 11 effect there is iEdge option. You can have iEdge 1 or 2. So those were non-linear stiffness contacts. Now let's look at linear stiffness contact, which can be node to surface or surface to surface contact. And today we'll talk about type 25. So similar to type 7 contact, type 25 is general purpose contact. Only the difference is this is linear stiffness contact, and you can see in this figure the stiffness is linear. So instantaneous stiffness is equals to initial stiffness. So in this case, the resistive forces will not depend on the rate of change of penetration. So when I say it does not depend on the rate of change of penetration, so it allows you initial penetrations. So this is also a single surface or surface to surface or node to surface contact, and it works again on the penalty method. A gap is defined around the main segment and the secondary nodes. You can see here this is your contact gap, and this contact gap is the sum of main gap and the secondary gap. So this main gap means the master gap, and the secondary gap is your slave gap. So when I say slave gap, it's the thickness of the slave component. As this is linear stiffness contact and does not depend on the rate of change of penetration, or the resistive forces are not depending on the rate of change of penetration, so it will not affect the time step. So for type 25 contact, you can have shell gap at free edges with the option I shape. So there are two options for I shape. I shape equals 1 and I shape equals 2. When you have I shape equals 1, you will have the square gap created. So this is your slave, this is your master. So this is as good as square gap, and the forces will be normal to the surface. And when you have I shape equals 2, that will create a round gap like this. And the forces will be normal to those nodes or the surfaces, or the forces will go in the radial direction. So just like type 19 contact, there is IH option for type 25 contact, and they're pretty much similar, but you have more options here to control the edges for shells and solids both. So when you have IH equals 0, so it will refer to the default card in the input deck, default card for interface type 25. So when you have IH equals 1, then the secondary and the main edges are external border edges of the shell segment as shown in this figure. Only external boundaries will be considered. So when it says only shells, there is this option is not for solid. So when you have edge option equals 11, the secondary edges are sharp edges of external solid segment and external border edges of shell elements. The master edges are all edges from external solid segments and the external border edges of the shell segments. So this is as good as having edge option 2 in type 19 contact. So it is going to consider all the edges. So you can have this option for shell and solids. So similarly, there are two more options, 13 and 22. And if you have IH equals 1000, that will direct you to default card. And if the default card is not defined, there will not be any edge to edge contact. So it's important to define default card or define the IH option in the contact. So that was linear stiffness contact, that was type 25 contact. And looking at those two different types of contacts, let's see what is the difference between linear and non-linear stiffness contacts. So this is the figure we saw in both the type of contacts. So non-linear stiffness contacts are 7, 11 and 19, and linear stiffness contacts are 24 and 25. In non-linear stiffness contacts, the interface stiffness is not constant and it depends on the rate of change of penetration. So here you can see the initial stiffness is K0 and it varies as the rate penetration increases, and your instantaneous stiffness will be KT. And in linear stiffness contact, you can see K0 equals KT. So your stiffness is always constant. So let's look at the example of crush tube. So this is simple crush tube, and the load case defined is initial velocity given to this crush tube for all the nodes, and it is given in the z direction, and the velocity is 13.3 millimeter per millisecond. So there are three models studied here. Model 1 is self-contact using type 7, that is nonlinear stiffness contact. Model 2 is self-contact using type 19, that is nonlinear stiffness contact as well. And model 3 is self-contact using type 25, that is linear stiffness contact. So when I run this 3 model, I have the results like this. But before going to results, this is how the contact card looks like in HyperWorks. So the leftmost is type 7 contact, middle one is type 19, and the rightmost is type 25 contact. So you can define your sets for slave and master. So for type 7 contact, my nodes are taken from these four components and the surface is taken from these four components. Similarly, in type 19 contacts, both the surfaces are taken from this set, and this set is made up of parts. For type 25 contact, again similar to type 19 contact, these surfaces are created from the parts, number of components. And these are the options which are a recommended option: ISTF, IGAP. You have to define gap mean, that will be always 0.5, and you can define any inactive option to compensate on initial penetrations, that is 6 for type 7 contact. For type 19 contact it is similar, 6, and for type 25 contact it is 5. And these are the results, and this slide shows the animation comparison between type 7, 19 and 25. So here you can see the behavior is almost similar. The way it is deforming, it's almost similar even if you take 7, 19 or type 25 contact. So this is animation comparison, and this slide shows you the rigid wall forces. So these are the rigid wall forces from your crush tube. So this is force versus time, and you can see here green is type 7, which is showing the maximum force because it is non-linear stiffness contact and the stiffness varies because of the rate of change of penetration. Below that is type 19, that is blue curve. It's almost matches with type 7, and type 25 contacts shows little lower force as compared to type 19 and 7 because it is linear stiffness contact and stiffness is initial stiffness. So having said that, let's look at advantages and disadvantages of linear and nonlinear stiffness contacts. So let's look at advantages first, and we'll look for nonlinear stiffness contacts first, that is 7, 11 and 19. So advantages are, this is physically correct representation. It gives you a high accuracy for describing the self contact and buckling, and it is best used with shells to shell and solid to shell interaction. So when I say it is physically correct representation means your rate of change of penetration will cause the resistive forces, and the simulation will be closer to the real physical characteristics. Let's look at the advantages of linear stiffness contact, that is 24 and 25. The advantages are, this is tolerant of imprecise meshing. So you can have initial penetrations or intersections in the model. Still it will work because we are defining the linear stiffness, and your instantaneous stiffness will be initial stiffness. It has formulation similar to explicit solvers, and this constant stiffness minimizes the effect of time step. So time step will not affect because of the type 25 contact. Now let's look at disadvantages of nonlinear stiffness contact. So it requires more stringent modeling practices. So you have to always take care of your meshing or the minimum element length and element quality. It does not tolerate the intersections or the initial penetrations. So you have to always make sure there are no intersection in the model. The time step may reduce due to increasing interface stiffness. So when there are a lot of penetrations, or there is a lot of rate of change of penetration happening during the simulation, your time step may go down. So when it happens, you have to always add the interface time step. And let's look at disadvantages of linear stiffness contacts. That is, result may not be as robust as compared to linear stiffness contacts. So let's look at few additional after looking at different types of contacts, let's look at additional tips and tricks. So let's look at sub interface or inter sub. So if you want to have force on a specific component by the neighboring components, you can achieve that with using inter sub option. So when you have a type 7 contact or a global contact defined, and you want forces on a specific component by the neighboring components, in that case you have to define this inter sub option. So in this example, let's say you have global contact here, type 7 contact, and in that contact you have these three different parts, and you're interested in forces coming onto this part because of the neighboring parts. Then you can define two separate inter sub options. So one will have this pair and other will have this pair, and you can see here, this is how the inter sub card will look like in HyperWorks. So the solver keyword will be inter sub, and in order to define that, you have to define the interface ID, and that is going to be your global contact. So we have to define this type 7 contact here, and master ID will be, or the surface ID will be, this master component, or the component on which you are interested to get the forces, and the node group will be the slave component, and the forces will be exerted from this slave on this master. If you want to look at how the workflow is, you can always refer to knowledge base article KB0117457 from Altair community page. You have to use that using your Altair 1 account. Let's check what is thickness at the part. So there are the cases when you have thickness more than the element length. So in that case, it is going to show you the initial penetration, especially you have thickness, let's say 10 millimeter, and your element length is 3 millimeter. So it is going to show you the initial penetration. So in that case, you can always use this thickness at the part option. So in the part card, you will always have this standard parameters, that is property, material, and along with that you can define optional thickness in this field, and this optional thickness will be just used for the contact gap calculation. So when you are using optional thickness in the part card, the physical characteristics of the model does not change if the thickness is changed in the part card. It will always refer to property card, and it will keep the original thickness for the physical characteristic, and only for the contact gap purpose your optional thickness will be calculated. So there will be no change in the total warnings and errors during the starter phase, and it eliminates initial penetration warning when you are using the lower thickness in the part card, because that lower thickness is considered for the contact gap calculation. And the computation time is almost similar when you use thickness for contact in the part card. So this brings to an end of this webinar. Thank you very much.